Hello, everyone. As Dima already said, my name is Gordienko, and he mentioned the name of my thesis project, and my supervisor is Joseph Martinez. So, for my thesis project, I did modeling of visual attention. Posner divides visual attention into 3 types, and in this project I will focus only on the orienting type of visual attention. So the type that selects what you are going to attend next, and it's typically divided into 2 parts. First is bottom-up attention. It's image-based and quite fast. And second is top-down attention. It's goal-based and slower. So there is a famous model of bottom-up attention by E.T. and Koch. It's based on the Treisman theory of feature integration, and in this model, visual input is analyzed in 3 parallel pathways: one for color, one for intensity, and one for orientation. Then these pathways are combined into one map. It's called Salience map, and it shows the likelihood of a particular point to be attended, judging only on the bottom-up attention. So image-based cues only. In my project, I build a combined model of visual attention. I use E.T. and Koch model as a bottom-up component, and then I add semantical influence to it. To do this, I use an open database of labeled images. It's called a Label Me database. So for each image, I have object identity information, so I know where this or that object is situated, and I know its spatial coordinates. So I can represent each image as a text that contains the names of the objects that are present on this image. Then I use an algorithm that's called Latent Dirichlet allocation. It's a Bayesian topic model algorithm that is typically used to estimate the similarity of the text and of words in the text. That's a generative algorithm that doesn't take into account the word order. So, as I already said, I have information about the objects that are situated on the image, and then I can run this algorithm on these texts, and as a result, get a similarity of objects. So, if I fix one object and call it target object, then I can draw an importance map. This map would show this similarity score, this semantic similarity score, and this map will be merged with Salience map from E.T. and Koch model, and it will result in a priority model or priority map that shows which point of image is likely to be attended, judged both on bottom-up and top-down attention. So once again, that's an architecture of my model. So bottom-up is E.T. and Koch, and top-down is my component based on Latent Dirichlet allocation. Then I made an eye tracking study to evaluate my model. So in this study, participants were asked to search for an object on an image. They weren't aware how many target objects are on the image, so they continued their search even if they found a target. Also, there were several images where there were no targets, and participants were asked to estimate how many targets they've seen at the image at the end of the search, and that's why we are aware that they really did this search task during the experiment. To evaluate my model, I used the same metrics as Turaba et al. Did in their paper. So I have a map. That predicts which points are likely to be attended at the image. Then I take top 20% of its area, which has the highest probabilities to be attended. And then I count how many fixations lays in this region. if my model would predict nothing, if it would be just a random model, the result would be 0.2. So I've evaluated how the Salience model alone predicted the fixations and how the combined model predicted the fixations. Results. Both models performed above chance, and my model performed significantly better. Sorry, I didn't mention that I had 2 blocks with 2 different target objects. One was painting and one was cup, and the second one was cup. So my model predicted fixation significantly better for cup target, and there was no significant difference for painting target. I explained it in this way. Carp is more specific in the terms of visual similarity. So cup happens where the tables are, where plates are, and painting could happen just anywhere. You can put a painting in any situation, and that's why the semantic information was more important for cup target than for the painting target. It's also important to mention that I've checked how model worked on the images where there was no target object, and it also worked, and the model for cup target also works significantly better. Donk and Van Zust in the paper showed that only first cases are driven by Salience, and the results of my model corresponds with these findings. So I've checked here on the graph. You see if the priority map was the score. If the priority map was better than the Salience map. When I estimate only data from first decade, from two first decades, and up to the sixth decade. You see that the first 2 decades, the priority model doesn't add any improvement, and then it comes to be significant. And there are several ways in which you can add the top-down information to the model. First group of biases is spatial bias. For example, images are more like pictures or paintings are more likely to happen in the upper part of an image than in the lower part. And then it's feature bias. If you search for the red sign that title shows when you're running out of time, your color channel would be prioritized. And third type is object-based or cognitive biases. For example, if you are making a sandwich, you will be attending a place where jam will appear in a couple of seconds. Thank you. Because you know that you are making a sandwich and you are going to put jam at this very point. And the other type, and it is my model, the semantic information, the information about object identities. So we're coming to the end of my presentation, and I'll sum up my results. In this project, I made a combined model of visual attention, and it predicted human gaze fixations better than the Salience model alone for cup target, and it didn't work for the painting target due to its generality in semantic sense. And also my model showed that first the cases are driven by Salience only, and the semantic information is more important a bit later. This brings me to the very end of my presentation. I'd like to thank Joseph McInnes for all the guidance and support during this project, and thank you for your attention. I'll be happy to